Hey Math Stars, good to see you. St. Patrick's Day, so I'm wearing my green, and we're going to go over a little bit of Taylor and Maclaurin series that we learned before break, and then we're going to go over four Taylor series that you need to have memorized. So we already talked about two before break, cosine and sine, but we're going to do a quick recap of those, and we'll talk about two more Maclaurin series that you need to be familiar with. So I don't want you watching this video like laying on the couch. Go sit at a table, get yourself a pencil and piece of paper, and do some work. Okay, so let's see if you can recall the general term for Taylor series. It's kind of loud here. The trash truck's going on outside. Got a noisy cat, so disregard any outside noise you might hear. Okay, see if you can remember the general term for a Taylor series. No, it's been a while. It's the nth derivative of f evaluated at c. C is where the series is centered. It's an x value that the series is centered around. X minus c to the n power over n factorial. Okay, as you know, a Maclaurin series is a Taylor series centered at x equals 0. Yes. So I want you to now go ahead and write down the general term for Maclaurin series. Okay, it's the nth derivative of f evaluated at the center, which is 0, x minus the center, which is just x minus 0, so it's x to the n power over n factorial. Okay, so as you recall, the day before break, we generated the Maclaurin series for cosine x. So the Maclaurin series for cosine x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And this is only equal to cosine x if it contains an infinite number of terms. So we're going to keep this going. See if you can remember the general term for the Maclaurin series for cosine x. So we need the signs to alternate. So we have negative 1 to the n power. We need the powers on x to, oops, this should be a minus here. My apologies. We need the powers on x to be even. So it's 2 to the n. And then we're dividing by 2 to the n factorial. It's an infinite series that's equal to cosine x. If I only wanted an approximation for cosine x, I could just do the first 2 terms, the first 3 terms. If I don't go on forever, this isn't a Taylor series. This is a Taylor polynomial. So we would call this the 4th degree Taylor polynomial centered at 0. For cosine x. So it's a polynomial because it's a finite number of terms. This is our Maclaurin series or Taylor series centered at 0 for cosine x. So just before we dismissed on Friday, we started generating the Maclaurin series for sine x. So how did we do that? We started with f of x equal to sine x, and then we just started taking a bunch of derivatives. F prime, f double prime, f triple prime. I encouraged you, once you get past that third derivative, to put a superscript of 4 there to indicate fourth derivative. Some people said they prefer to write 4 primes, but that's a little bit easier way to denote the fourth and the fifth derivative. After we had all those derivatives, we inputted a 0. So I'm going to let you go ahead and just do that, just to get a little bit of practice. So go ahead and pause the video. And then try to formulate the Maclaurin series. It's a Maclaurin series because it's centered at 0. The Maclaurin series for sine x. Okay, so I'm going to go ahead and I'm going to pause the video and I'm going to generate all of those, and then we'll formulate the series together. So notice that when n is equal to an even number, 0, 2, 4, that those derivatives are equal to 0. So we're only needing the odd derivatives. So if we just continue this pattern a couple more, just so we have more terms for our Maclaurin series before we write our general term. So the 7th derivative would be, again, a -1, and the 9th derivative evaluated at 0 would be a +1. So as you recall, looking up here to our general term for our Maclaurin series, we're going to formulate our series by doing the 0th derivative evaluated at 0 times x to the 0 over 0 factorial. The first derivative evaluated at 0 times x to the first over 1 factorial. Write out a few more terms. This is really good practice for you just to be more familiar with the formula for the general term for Maclaurin series. So go ahead and pause the video, and then you can resume it, and I'll write out the next couple terms. Okay, so now let's go ahead and input our derivatives into the formula that we wrote out there. So f of 0 is 0, so this first term just becomes 0. The first derivative evaluated at 0 is 1, so we have 1 times 1 to the first power over 1 factorial. Second derivative is 0, so that's a 0 term. Next one is a -1 x cubed over 3 factorial. We already talked about how the 4th and the 6th and the 8th, those are all going to go to 0 also. So the even powers of x become 0. So we're going to get rid of those. So let's just continue our pattern with the odd powers of x. Okay, I'm going to do a dot, 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 and then we need to write our general term. So when n, let me see if I have a little space up here to write. So I'm going to go up here. So n is just the counting numbers, 0, 1, 2, 3, 4. So if I take 2n, like we did with cosine, 2n is always going to give us the evens. So if I add 1 to 2n, if we add 1 to all of the even integers, that's going to give us odds. So we're going to use a 2n plus 1 down here to get our odd powers. So our general term for the Maclaurin series for sine is still alternating. So we still have the -1 to the n. And then we have x to the 2n plus 1 power over 2n plus 1 factorial. And then this continues on forever. So we do a dot, dot, dot. Okay, let's go ahead and pause here. Okay, let's have a little conversation about even and odd functions. And then you guys are going to formulate the last 2 Maclaurin series for functions that you need to know. So an even function some examples of an even function would be like x squared, x to the fourth, any polynomial where all the powers of x are even. Cosine x is also an even function. Here's a couple of things that are special about even functions. F of negative x is equal to f of x. So when you input, say, pi over 2 into the function, that's equal to the output when you input a negative pi over 2. Or if you input a negative 2 into a function, you get the same output as if you were to input a positive 2. So even functions are symmetric over the y-axis. So cosine x is an even function. That's why in the Maclaurin series for cosine, all of the powers are even, because it can be described by an even polynomial. Okay, an odd function. Some examples would be x cubed. Even the cube root of x is an odd function. Sine is an odd function. Odd functions, they have the identity that f of negative x is equal to negative f of x. So when you input, say, a negative 2 into the function, it has the opposite output, opposite sign on the output as if you were to input a 2. These guys are symmetric when rotated 180 degrees around the origin. Symmetric when rotated . Okay, so because sine is an odd function, it can be approximated by a polynomial that's odd. All of the powers of x are odd. Okay, so I would like you to formulate 2 more Maclaurin series. The first Maclaurin series I'd like you to formulate is for f of x equal to e to the x. So just recall, you're going to be finding all of your derivatives, several derivatives here, and you're going to be, we're doing Maclaurin series, so you're going to be evaluating all of those derivatives at 0. And then what's our general term for the Maclaurin series? Let's see if you can remember. General term for the Maclaurin series? Jot it down, see if you remember. The nth derivative of f evaluated at 0, x to the n over n factorial. So I want you to formulate the Maclaurin series for e to the x, including the general term. And then the last one is I'd like you to formulate the Maclaurin series for 1 over 1 minus x. So I'll record myself formulating these, but I want you to pause the video and go ahead, you yourself, try to formulate the Maclaurin series for each of these functions. Write it out with several non-zero terms and then include the general term. Okay, so let's see if you're successful at formulating these 2 Maclaurin series. So all of our derivatives evaluated at 0 of e to the x are 1. So using our general term for Maclaurin series, the nth derivative of f evaluated at 0, x to the 0 over 0 factorial. Oops. X to the n over n factorial. Okay, so let's go ahead and do this. So we have 1 x to the 0 over 0 factorial plus 1 x to the 1 over 1 factorial 1x squared over 2 factorial. So this guy's kind of cool. So we can write it out again, more simplified. So e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. The general term for this guy is super easy to write. X to the n over n factorial. Okay, so again, this is the Maclaurin series for e to the x. It's an infinite series. If I wanted, say, the second degree Maclaurin polynomial for e to the x, that would be e to the x is approximately 1 plus x squared over 2 factorial. It's an approximation. It's a polynomial with a finite number of terms. Okay, let's go to this guy. He's really fun. So I hope you remembered when you took your derivatives here to use chain rule. If you got stuck and you were doing quotient rule and it was really hard to do, go ahead and do chain rule to take the derivative of this. So, bring the power to the front, subtract 1 from the power, multiply by the derivative of the inside. Okay, these two negatives turn into a positive. Okay, let's do the power rule again. So -2, 1 minus x to the -3 times derivative of the inside is again a -1 because we're doing chain rule. Of course, those negatives give a positive. Okay, taking the derivative again, so we get -6, 1 minus x to the -4. Chain rule. Again, the negative times the negative turns into a plus. And let's do one more. So bringing that 4 to the front, we get -24, 1 minus x to the -5 power times the -1, two negatives, multiplied to give a positive there. Okay, hope that's big enough for you guys to see. Okay, let's go ahead and input a 0 in here. So inputting a 0, I have 1 to the -1 power. 1 to any power is just 1. Inputting a 0 here, I have 1 to the -2 power. 1 to any power is just 1. So 1 times 1 is just 1. Okay, inputting a 0, again, 1 to the -3 power is just 1 times 2. 1 to the -4 times 6. And then 1 to any power times 24 just gives 24. So again, if you are not able to get this far on your own, go ahead and formulate the Maclaurin series for this function 1 over 1 minus x and write the general term, please. So pause the video and go ahead and formulate that. Okay, I'm going to keep going. So again, we're using the formula for the general term for Maclaurin polynomial, which is the nth derivative evaluated at 0, x to the n over n factorial. Okay, so starting here, we have 1 x to the 0 over 0 factorial plus 1 x to the 1 over 1 factorial plus 2 x squared over 2 factorial plus 6 x cubed over 3 factorial plus 24 x to the 4th over 4 factorial. Okay, so let's see what we have here. So we know that 0 factorial equals 1, as does 1 factorial. 2 factorial is 2. Multiply by 3, we get 6. Multiply by 4, we get 24. So these coefficients, or these values of our derivatives, are just the same as the factorials. So this term just simplifies to be 1 plus x. 2 factorial and 2 are the same, so they cancel out and give x squared. 3 factorial is the same as 6, so that cancels and gives x cubed. 24 and 4 factorial are the same, so that's just x to the 4th. So the general term for this one's super easy, x to the n. So this is the Maclaurin series for 1 over 1 minus x. So again, because we listed out all of those terms and we keep our series going forever, we can say that this rational function is equal to this series. Okay, so look for another video soon that has some notes with Taylor series. But this was just like what we were going to do in class after we got back from break. We were going to kind of formulate these series together, and these 4 you have to have memorized. So you might want to pull out your formula sheet and add these 4 to your formula sheet, because these are the 4 that you have to have memorized. But I'll probably send you guys a picture of that formula sheet once I add these to mine. All right, thanks for participating. Hope you worked hard, Math Stars. See you later.